Good morning, class. This is the video for the September 8th and September 10 lectures. And as I've written here on the blackboard, we're going to finish up our sort of light discussion of semiconductor physics, what you need to understand for purposes of the course here, which, going beyond the handout, are sections 2.4 and 4.3.6 in the textbook. And you can see that very nicely. I have a little screen here, and I'm able to project the a PDF of the textbook, and so be able to refer to it as I'm going forward, going through the material here. First, a little bit of housekeeping with regard to all this. It's unfortunately I have to sort of stay off to the side here and refer to things on the screen. I can't directly go and point to things because my webcam tends to lose focus, and this is an ongoing problem. I'm not sure what to do about it. Ultimately, I guess look for a webcam that somehow has a different sort of autofocus that doesn't get messed up. But anyway, if you'll have to bear with me that I'm sort of going to stand off to the side here. As we go through these sections, I may write something on the board here, but I'm staying over here so that I don't mess up the focus of the camera. All right, and after we do that, we're going to start with the actual, sort of fabrication material of the course, which starts with thin film deposition, and we'll explain what a thin film is, and that's in these sections here. Now, again, a little bit of housekeeping before we go forward. I'm going to be very careful to limit the like what's written in the syllabus, the sections. All right. You'll notice that there's a lot more material in the textbook. All right, and it's great material. It's a great textbook. I highly encourage you to look at it and derive value from it. But the point of listing these sections is that there will be nothing on any homework or exam that's not covered in these sections, and that's the point of them. Especially the way we're doing things right now, I want it very well defined what I am expecting you to learn and be able to return to me in any sort of homework or quiz. So with that being said, let's just get started here and finish up our section on semiconductor physics. So I have my one computer, and let's jump down to, oops. And so what we'll do here is we'll do that, and I'll keep track of what I can see on my computer screen, and you can see it too. And I think I covered this in the handout. He uses rho. Sigma is one over rho, where this is the resistivity and this is the conductivity, and even the words sound like, okay, we know that one is the inverse of the other. And so you can see that taking one over that's n. Now he uses Q. I make a point of using E, and the reason why is that the charge of a carrier is always E. All right, whether it's a hole or an electron, it's 1.6 times 10 to the minus 19 coulombs, and that's important to realize and understand. It's unlike the effective mass, right, which you've learned the effective mass can be, different. Whether it's a hole or an electron in any semiconductor, it's always E. So I use E particularly, and then mu. All right, and so it connects with the handout, and he has some useful tidbits here. Where was it? Okay, yeah, he writes it right there. And again, I'm not gonna point to the screen because it messes up the focus and it's a real problem. So I'm just going to read off the screen here with you. Mobility decreases with increasing carrier concentration. All right, and that's helpful to know because, of course, if you were increasing the conductivity, you would increase N, which you would do by increasing the doping. And so you might expect that if you increase the doping, that the conductivity will go up linearly, and it doesn't. It goes up a little less than linearly because as you increase the doping, the mobility goes down. And I think you can understand the reason why, because you understand that mobility is proportional to the scattering time, which makes sense because the longer the scattering time, sort of the more mobile the devices are. And it's just sort of naturally to understand that that one of the things you can scatter off of are the dopant atoms themselves. And so the more dopant atoms there are, the lower the mobility. And this is an example of, the kind of things, and again, you could not watch these videos and just read these sections and understand everything in each of these sections and be fine on any quiz or homework or anything like that. But I'm making a point of particularly that because that's the kind of thing, that's the kind of question I might ask in a quiz, all right? And in fact, I think I will, in the first quiz, maybe I'll ask, okay, does the mobility go up or down as I increase the dopant concentration? So, during these videos, I'm pointing out things, and that's communicating to you that I think it's an important thing, and that you should understand it. All right, now beyond that, basically this section is on how to measure the conductivity, and we can walk through this a little bit. This equation here is just how you connect resistivity or conductivity to the actual resistance. And, oops. And so if you have an actual piece of semiconductor with a width and a length and a thickness T, the resistance is given by that formula. And he introduces the concept of something called the sheet resistance, which is works out to the resistivity divided by the thickness. And the reason for all this is because you need to understand that there's a device in the clean room that you would use to measure what the resistivity or conductivity of your material is. And it's called a 4-point probe. You may ask yourself, well, why can't you just use a 2-point probe? I mean, the idea is basically to use an ohm meter to a certain extent to measure the resistance. The reason why you use a 4-point probe is because you send the current with the outer probes. All right, you can see the current is sent by the outer probes, and you measure the voltage across the wafer surface with the inner probes. Now, here's where, okay, for example, I could give you a whole handout, and we could do a 30-minute derivation of what V and I are in terms of the resistivity. And he works it out for you. The resistivity is given by this formula, where if in your probe, okay, now for that formula to work, the needle spacing has to be the same. Again, the outer needles are sending current into the semiconductor, and the inner needles are measuring the voltage developed across the semiconductor due to that current flowing. And then this is the formula relating how you derive resistivity from V and I, given a certain thickness of the semiconductor. And so now I guess this if we were teaching a normal course, all right, first of all, I mean, you can perform this derivation. Like I say, we could spend 30 minutes deriving that formula. We're not going to do that, which means that, okay, if we were teaching a normal course and I would be giving closed book tests or exams, I mean, you might ask yourself, well, do I have to memorize that? And that is one simplification for what we're doing now. All quizzes are open book. And so if I ask you a question about a 4-point probe, you can just open your book to this section. So this is more along the lines of teaching you what you need to know to operate in the clean room. And if you were operating the clean room, one of the first things you might want to know is what's the conductivity of my wafer. And so this is how you measure that. Just stepping back from that, I mean, you usually order a wafer with a particular conductivity. Like you would go to Virginia Semiconductor and order a wafer of silicon that has a conductivity. Now the thing is that what Virginia Semiconductor would tell you is that this wafer has a conductivity anywhere between 10 and 100 ohms, 1/ohm centimeter. And so you have to, and that's because when they fabricate the wafers, there's a variability in how much dopant exists in the wafer that they can't specify any closer. And so it's up to you then, once you get the wafer, to pin down, okay, the conductivity is really 23, and so this is the device that you use to measure that. So I guess, along the lines of things you need to know or things I'm expecting you to understand are that this device works, that there's something called a 4-point probe, and there's a formula for how you determine conductivity of your wafer from it. And actually, do we have one in Sierra 120? I'm not sure. But I know we have one in one lab in the building. All right, and that kind of is really all I was getting at in that section. I don't want you to, you don't need to worry about other stuff here. The point of covering 2.4 was knowing that there's a device called a 4-point probe and how you determine conductivity from it. Now jumping ahead then, in our semiconductor physics, we go to 4.3. And you can see that 4.3 is in the chapter labeled silicon, and so there's all this discussion about silicon. And for example, this table here can be very useful, because if you needed to know anything about silicon, like its thermal coefficient, the coefficient of thermal expansion, for example, I mean, you could get it there. But what, and it talks about, we talked about in one of the lectures, or one of the group me sessions, how you fabricate wafers. But in terms of semiconductor physics, I mean, this is particularly the you need to understand something about crystals. All right, so this is the crystalline structure of silicon. Now, in terms of this course, see, if we were teaching actual semiconductor physics course, we would spend a lot of time on this and understand things like, you know, the bonding and, you know, what type of crystal it was and things like that. If you're interested in that sort of stuff, I digress a little bit here, just because it is kind of interesting stuff, and maybe I can do it this way so that I don't mess up my focus. What you will see is that each silicon atom here is bonded to 4 other silicon atoms, and so when we were talking about, you know, N and P and doping, things like that, I drew the 4 atoms around a silicon atom in a plane, and you can see that was just schematic. This is what they really look like. For those of you that are really interested in semiconductor physics, one of the things that's always fascinated me is that that quantum mechanics, if you've taken any quantum mechanics, you know that, or even, well, really even chemistry, you know that there's mixed quantum mechanical states called sp3, which are tetrahedral. That if I solve for the quantum mechanical wave functions of an atom, it will give me lobes on a tetrahedron structure. And so, for example, if you were to look at a molecule like methane, okay, CH4, that it would be on a tetrahedral structure. And so when I form a solid of silicon, it also has that sp3 orbital structure, and it just naturally falls into place in a crystal. Meaning, you know, you can think of like these 5 atoms here being a molecule of, you know, Si5. Okay, here's the 1 and then the 4 bonded to it. But it works out that quantum mechanical result of the wave function being tetrahedral lends itself to bonding in this crystalline structure shown here. And it's and you can see now, okay, so that's kind of the molecular discussion, this tetrahedral bonding. And now let's talk about the crystal. Okay, you can see that atom, there's this thing called the unit cell of the crystal. And the term A here is very important. That's the lattice constant. And so the atoms naturally fall into sort of a cube. And then, of course, this is repeated infinitely. And you can see, going back to our atom here, this one here is sort of suspended inside the cube. And he's bonded to ones on the corner and on 3 faces. See, this one is on that face. This one is on that face. And this one is on that face. Oh, I guess when the guy made this diagram, he was trying to focus on this quote-unquote molecule. That's my cat. Stop that. And so this is what's called a diamond structure. It's also called a face-centered cubic structure, because the atoms not only are at the vertices, are at the corners of the unit cell, but they're also at the centers of the faces. Things to know here. Well, do I want you to do this? Well, it's just sort of fun. you can take this diagram and you can come up with the density of silicon. Because you add up the number of atoms in this box. Now to do that, you have to realize that, for example, this atom here has 1/8 of itself. Oops. 1/8 of itself in the box. All right, think about it. He's at the corner, and so he's got 1, 2, 3, 4, 5, 6, 7, 8. He's also in 7 other boxes. All right, and you have to draw this, and I don't want to belabor this point, but it is one of the things that are useful to know. So this atom contributes 1/8 of itself to the mass inside this box. And this one, of course, contributes all of itself because it's all inside the box. These ones on the faces contribute half of themselves because they're half in the box. And if you add them all up, what he says here is that there's 8 total silicon atoms inside this box. And so if you wanted to calculate the density of silicon, you could take the mass of silicon, mass of a silicon atom, multiply times 8, and divide by A cubed. All right, I know that's a lot of discussion with no accompanying drawing on the board, but I think you can follow it and go from there. Now, and so that's kind of a neat thing you can do from those pictures. This is actually kind of what's more important to this course here, which is that you can talk about 3 particular planes of the crystal. Again, the crystal is these boxes, repeated infinitely, each one stacked up together. And so you can talk about 3 planes of the crystal based on these boxes. The first plane is the plane of the faces themselves, and then that's called the 100 surface. The second plane, which is not used very often, is this plane here, which sort of connects 2 sides of the box, and that's called the 110 plane. And you sort of get the idea that it's 100 because it's only one. It's 110 because it connects 2 sides. And then a third plane, and it tends to be this plane and this plane that you actually use, is where you connect the opposite vertices like this, and that's called the 111 plane. And when you order a silicon wafer, I forget whether he has a picture here of that. Not really. All right, so I just have to, actually maybe I will draw a picture. So let me do it this way. Okay, take my semiconductor wafer. All right, and let's zoom in on that surface. So I'm zooming in, actually you can't see the bottom surface, I'm zooming in on the surface. And so if it were to be a 1, 0, 0, then it would look like this. Meaning, it's like I took, and I'm not going to point at the board because it'll screw up my focus. If I took those boxes, and those boxes were just stacked up against each other in a surface, that would be a 1, 0, 0 plane. And so that's, of course, the easiest to understand. And if alternatively, and let's see if I can draw something helpful. Okay. So I can't draw it. You know, the 1, 1, 1 is that plane there. All right. I'm not going to try and draw it, but you have to imagine that, like the 1, 1, 1 picture there, you have to imagine that gray shaded plane, that for a 1, 1, 1 wafer, that would be the surface of the wafer. Okay? So try to think of it that way. And now, why would you pick different crystalline structures? Well, I mean, it just turns out that, for example, if you fabricate different types of devices, you're usually concerned with, you know, conductivities in the plane and things like that, or different types of crystalline effects that occur, and so you might pick one crystal plane to be your surface versus another one. Now you can you get the idea that the 1, 0, 0 is kind of the most straightforward surface to work with, and is usually the one that is so. All right, now we could get all into vectors, and you know, again, you're going to have to listen to what I say here. That you know, I don't want to make this unnecessarily complicated. If we were teaching a course in semiconductor physics, we would talk all about vectors and crystals and things like that. That table there to the right, you know, that's, you know, we discussed that. You fabricate an ingot, which is basically kind of a cylinder of the crystal, and then you use sawing. So that's the wafering process. But in terms of section 4.3, understanding, you know, especially what he says here, the two crystal orientations mostly used in fabrication are 1, 0, 0 and 1, 1, 1. And you now know the meaning when those are said. All right, the wafering process, we've gone over that. I mean, you take this sort of cylinder of silicon that you fabricate, and you then, you know, saw wafers, usually not that thick. Wafers are usually on the order of 0.5 millimeter thick. And oh, this is okay. So this is a nice picture showing the surface of a wafer. And this would be a 1, 0, 0 wafer because that surface is in the plane of the surface. And you get the idea. It's hard to draw a 1, 1, 1 wafer. Now, this is also something that's kind of important to realize, that you can order wafers for fabrication upon which are called miscut, which means that the surface is not exactly in, for example, the 100 plane. And it might talk about the wafer being, you know, if I took my boxes here, that I might fabricate the wafer by sawing at a very small angle, which, you know, with the angle I've drawn is extremely exaggerated. But when I did that sawing process shown in the other figure, I might do it, I might cut it at a very slight angle. And the reason for that is because, you know, it may sound, you know, kind of not good, right? Because if I saw it exactly at the crystal plane, which I can do, okay, I get exactly a crystal plane on the surface. You may think that's more desirable. Well, for some devices, it's actually desirable to have the surface broken up, so to speak, so that it's not one single plane all the way across, and that can lead to better properties of devices that you fabricate to have the surface be not exactly in the plane. So that's called a miscut wafer, and there are various reasons for doing that. And various things here. I don't expect you to know these equations on roughness, things like that. But let's talk about table 4.4. See if I can bring this over here. Now, here the author of the textbook gives away his particular research area, which is in what's called MEMS, micro electro mechanical systems. MEMS. The author of this textbook is obviously a MEMS researcher. We might talk about MEMS a little bit more later in the course. It's not a focus of the course. A MEMS device is a device that where you are fabricating a particular mechanical structure. There are mechanical structures, MEMS devices that you fabricate that have sort of static and dynamic mechanical structures. The best example of a static MEMS device is the print head in your inkjet printer. If you ever look at the print head of your inkjet printer, you'll see that it's actually a chip. And it's a chip that has basically little mechanical structures etched into it so that it can convey the ink. The next example of a dynamic MEMS chip would be the accelerometers in your phone. Basically, the accelerometers in your cell phones are chips that have little freestanding mechanical features etched into them, so that when the phone is tilted at different angles, those little mechanical structures move slightly from one side to another and change their electrical properties, which can be measured by the chip. But anyway, we may come back and talk about MEMS a little bit more, but it's not a focus of the course, but obviously it's a focus of this guy here. So he has two columns there, and what he's saying is that there's different, and it is an illustration, there's different particularly ideal wafers for whether you're fabricating an IC, meaning an integrated circuit with transistors, or a MEMS device. And but this is the kind of, if you go to, like, again, some silicon wafer vendor on the web, you'll see a set of specifications for the wafer. Some of them are easy to understand, like thickness down there. Again, 525 microns or 380 microns. It's around a half a millimeter, and so you kind of have an idea how thick that is. As mentioned, like resistivity there, you can see that when you buy a wafer, it specifies within a range what the resistivity is, like 16 to 24 ohm centimeters. And so if that amount of uncertainty were okay to you for whatever you're fabricating, you'd be fine. But if you needed to know, for example, to within an ohm centimeter what it actually was, you'd have to go use that 4-point probe and do that measurement. Orientation, we just covered that, 100. And then there's basically other considerations. This one is kind of important, not the front side. Obviously, the front side is always going to be polished because you have to fabricate your devices on a pristine surface. But the back side of the wafer can be either polished or what's called etched. And if it's polished, I mean, essentially you can fabricate devices on either side. If it's etched, obviously you can't. Etched, means you have a sort of a roughened surface on the back. And maybe in the next video, I'll go on campus and get a semiconductor wafer so you can understand what these things mean. Really the nice thing about having a wafer whose backside is etched is that you know which side is back. I mean, you can get into situations where both sides are polished and you start fabricating on one side. You may not be able to tell which side you've been fabricating on. So it's nice to have. Sometimes it's nice to define basically a front and back side that way. Okay, and let's see what else you got here. I guess the various things he talks about in here. He talks about defects. We don't need to. I mean, most of the time, as far as you're concerned, a defect is a defect. But we can walk through this fairly quickly. Do that. Make it a little smaller. So I'm just going to sit here and okay, and I realize that it's difficult to read, but you do have the textbook, and so you can do this for yourself. Let's look at an easy one here. Okay, so that's basically, that could be a dopant atom. That it's basically a dopant atom is essentially a defect, right? Because it's not the crystal, and so if you put a dopant atom there, it could. Now what he has drawn here is usually a dopant atom doesn't make that distortion of the lattice typically, because it just sort of fits in the lattice and doesn't cause this distortion. But you get the idea, that can be a dopant atom. There are okay, G here. G is basically a vacancy. That's where there's a missing atom in the lattice, and so that's easy to understand. C is where there's an extra atom. And you can just sort of walk through these here. A is fairly common. It means that there's an atom sort of within the lattice that's not supposed to be there, and that is typically hydrogen. Hydrogen is everywhere in the world, and so you may get hydrogen embedded, and of course hydrogen is a small atom embedded in your lattice. And so, you have these various types of defects that occur. and each one reduces your mobility, is the way to think about it. All right, and you know, he goes through here the various reasons why defects may occur, and that was all right. Oh, I did have 4.6. Why did I have 4.6? Oh, that's why I had 4.6. Okay. This wafer here. Okay, so the wafer on the right here. Let's see if I can make this bigger. I'm just checking my focus on my other computer here and making sure I'm not messing up. This wafer on the right is called silicon on insulator, and the way you fabricate this is okay. So you have to think of this is fairly thick. This is like 0.5 millimeter thick. This down here, and then you have it could be a 1 micron thick layer of silicon dioxide with a 1 micron thick layer of silicon on top of it. And how you fabricate that is through what's called wafer bonding, which we may be able to cover later on in the course. But the point is, you can buy a wafer like this that has a buried layer of silicon dioxide, and it's called silicon on insulator, and it can be very handy. For example, it allows you to fabricate individual devices in this top layer that are electrically isolated, because silicon dioxide is an insulator, whereas your silicon down here is typically a conductor. So that was the reason for including 4.6, is I want you to be aware that there's this type of wafer called silicon on insulator. Okay, and that sort of or does complete our section on, you know, sort of the semiconductor physics we have to know. And the only the only part that that I went over just now that might require a little additional development is, you know, that business of figuring out how many atoms are in the lattice in order to calculate the density, and so the way I may handle that is by assigning as a homework problem, and so you'll learn how to do that. Okay, and now we begin our discussion of how you actually make this stuff. And here I'm going to kind of reiterate these different different ways of thinking about that. Where are we here? This is table contents. Oh, picture. Okay. So, again, which I've discussed before, using this analogy, and it can be a useful analogy to talk about fabricating semiconductor devices analogously to fabricating dishes in the kitchen, food dishes like making a cake or making a casserole or something like that. There's sort of two lesson plans, so to speak. So if I were to teach how to make something in the kitchen, all right, what I could do, and what we're doing now here, is have a set of lessons on, okay, chapter 1, how does the oven work? Chapter 2, how does the microwave oven work? Chapter 3, how does the mixer work? Just coming up with things off the top of my head. And sort of, walk through how the various pieces of equipment and processes you do in the kitchen work. And, that's what we're going to do. And for example, well, we'll get back to that. But, certainly for teaching you how to cook, that would be very boring. And to a certain extent unnecessary. And so I've never taken a cooking class, but I imagine it just starts directly with recipes. Assuming you understand, how to operate the oven and stuff like that. So, the other lesson plan that we could do here is, okay, chapter 1, how to fabricate a laser. Chapter 2, how to fabricate a MOSFET, And the thing is that, and that's what you would do in the kitchen, but it doesn't work here, because whereas in the kitchen it's pretty obvious how the oven works, here it's not at all obvious, and you have to go through a lot of understanding to know, for example, how an optical lithography mask aligner works. And so what we're going to do in this course, my idea here, is that we're going to go through these sections in the syllabus of, okay, how you do thin film deposition, how you do epitaxy, how you do lithography. Each one is a chapter on, a process that you have to go through in the clean room and the associated equipment and how you operate it. Then after that, we're going to go back and go through particular recipes. So we're going to do it both ways. First, learn how all the steps of a recipe work, and then go through some recipes at the end of the course. And that's the concept here. So, I'm just saying that so that, if you think it's not particularly fun, what we're doing, that's the methodology, and that's why we have to do it. You have to learn each of the process steps before you can perform a recipe here. Okay, and that being said, he has a set of, I don't want to mess up the focus, he has a set of chapters here on different things you do in the clean room. Now, one thing about the textbook, again, I like the textbook. I like it because he has a lot of useful material in it. But it can be a little bit disjointed. And for example, you see, as I'm going through thin film deposition, I'm going to start in section 5.2. And at one point I have to jump up to 7.5 because that's where he put that relevant piece of information, and then back. And so there is a little bit of back and forth, and just bear with that. And you'll, I hope, see as we go through the method in that. Now, after teaching this course for the first time a year ago, I realized that it's a really boring course simply because, okay, standing up here and walking through how an evaporator works and showing a picture of it in the book and describing the steps of performing it and things like that is just really, really dry. And so this summer what we've done is we've recorded a set of videos of one of our graduate students actually operating equipment in our clean room, so that augmenting what I'm doing here, you actually can see him, and he's really good. It's very, very, very nice, very professionally done, and Nam did a great job discussing what he's doing, and so you'll see in the syllabus, like in this section here, there's also some videos that you're supposed to watch. They're not long, they're like 20-30 minutes. They're fun to watch, they're very nice. Unfortunately, they aren't up on Canvas yet, and I'm working on that. Actually, I'm not working on that One of the people from media services is working on that, or Canvas services or whatever. They're too large to put in the file section. They're about 5 gigabits total, and you only get a gigabit in your file section on Canvas. And so they're working on putting them in the My Media section of the Canvas page so that you can access them there. All right, now with that preface, let's just get started here, and go to section 5.2. So, what thin film deposition is about is, and I'll first just draw it as a blanket deposition. Okay, so you have your wafer, and you want to deposit what's called a thin film on it. And why would you want to do that? Well, okay, so that's, getting into this, okay, whether I'm teaching you recipes or recipe steps. And so all I'll say right now is that a certain recipe for a particular semiconductor device may call for depositing a layer of material. Now, you can imagine that if that material is a metal, well, you're probably doing it because you're forming contacts or something like that. And you might have seen pictures. And again, I'll bring the semiconductor wafer next week and show it in the video here so you can see these various things. But you've probably seen pictures of integrated circuits, for example, with a whole bunch of metal all over it, because it has to have circuits on it and conduct things. Now, so okay, so what I'm kind of showing here is, all right, taking your wafer and just blasting some material on it and forming some layer. Now you get the idea that in conjunction with other process steps, you don't want it covering the whole wafer. You want like little stencils and patterns and things like that, and we'll get to that. But this is what we sort of chose to start with first is this step, this recipe step, this process step, and now there's various ways of depositing a thin film. First of all, a thin film. What do we mean by thin? Well, okay, a thin film might be a micron thick. Recall a micron is 1/1,000,000th of a meter. Okay, so the wafer itself, may be 500 microns, and the thin film may be 1 to 10 microns. So that's what's meant by thin. All right, and those are just examples. A thin film can be as thin as 100 angstroms. It can be very thin, and so there's and if I could just jump ahead maybe. Okay, there's kind of two categories of thin films. There's metals, and there's what's called dielectrics. Um, and then over here, there's okay, physical vapor deposition. Um, okay, well, evaporation or sputtering. I know that's hard to read, and you need to like listen to me more because I just have only so much space here to operate. But those are forms of physical vapor deposition. Physical vapor deposition means taking your material that you want to evaporate, that you want to deposit, and somehow forming a vapor of it, which can either be by evaporating it or doing what's called sputtering it, so that, and we'll try to show pictures in a little bit, so that the material forms a vapor. Now, of course, this is in a vacuum chamber typically. Metals tend to be done that way. Okay. Now then there's chemical vapor deposition. And dielectrics tend to be done that way. So that's the most general way of categorizing thin film depositions, is that there's metals and dielectrics, and metals tend to be done by physical vapor deposition, and dielectrics tend to be done by, and we'll get into what chemical vapor deposition is. And now, there are lots of times where you may deposit, in fact I've done it plenty of times, you can deposit certain dielectrics using physical vapor deposition. And you can deposit certain metals. Well, actually, let me think about that. I mean, you could by chemical vapor deposition. It's very unusual. Okay, let me just fix this. That was my cat. Okay, and let's just start walking through it. So physical vapor deposition is what here's a nice picture here. Let me make it a little bit bigger. Maybe I can't make it that big. Maybe I can. I can. All right. So, now, what you're gonna, one of the videos is on using what's called an evaporator, which is what this picture is basically showing, is the process of evaporation. Again, there's two types generally of physical vapor deposition. There's evaporation, and there's what's called sputtering. And this is showing evaporation, and it's particularly showing evaporation using, oh, I can't do that, I'll go out of focus. It's showing evaporation using what's called electron beam heating. Now, what's happening here, this is maybe the the wrong way to start with evaporation, because it's sort of easier to understand with what's called resistive heating. So what I'm going to do here is evaporation and I'm going to put in parentheses thermal. So thermal evaporation would be this. Okay. So you have a vacuum chamber. Okay. And somehow you've suspended your wafer up here. That's a horrible drawing of a wafer. I'm trying to draw it. Trying to draw it so as if you were seeing it. Kind of the back surface. Let me just do it that way. You get the idea. All right. So this is thermal evaporation, where basically you run a current through what's called a crucible, or usually it's called a boat in thermal evaporation. And basically you've put in your material here, which could be some metal, for example. And you start evaporating it. It's very simple. You tend not to think of evaporating a metal, but it's just like anything else, like water. I mean, if you boil water, it starts evaporating, and if you essentially boil metal, now of course you have to go to a much higher temperature to boil metal, but the idea is that basically it starts evaporating and starts sending atoms up toward the wafer, which you've suspended somehow, and so you start depositing your thin film. So I'm drawing at this, what he's showing in the textbook. What he's showing in the textbook is that instead of heating the metal by passing a current through it, you can heat it by using what's called an electron beam. And I'll get to that in a second. And the thing is, while electron beam evaporation is far more common, thermal evaporation is sort of easier to understand because of the word thermal. You're boiling the metal essentially. When you're operating an evaporator, you actually usually have a viewport, and you can look at this thing. It doesn't look like it's boiling in the sense of like water, boiling. It looks usually, ideally anyway, fairly serene in terms of course, it's glowing bright white, but it's just sort of liquid. All right, it's not like you're aggressively boiling something. You're just heating it up sufficiently that, okay, it's able through thermal energy to produce an evaporated component, a vapor. And that's why it's called physical vapor deposition, because you're physically producing a vapor that you use then to deposit your thin film. Now what he's showing in the textbook there, again, is called E-beam evaporation. And all that means is it's where instead of heating, and again, this is basically heating this crucible by passing an electric current through it and just making it really, really hot. And over there, instead, he's heating it by firing an electron beam at the crucible. And there's various reasons why you use electron beam heating than thermal heating. Here, I mean, there's a lot of this is a good example where semiconductor processing does sometimes resemble cooking in the kitchen in the sense that different cooks have different, ways of doing things that they prefer. Now, for example, as you can see, this textbook is basically teaching, I forget if he even talks about thermal evaporation, of using E-beam heating in order to do physical vapor deposition, evaporation. Now, me personally, if I were evaporating gold, all right, I would use thermal, because I know that I've tended to get better gold films using resistive evaporation. Of course, e-beam works just fine. It's just that I mean, people tend to have their preferences a little bit. Now, where theory comes into play here a little bit is that um, you know, getting back to our analogy that you're boiling a metal, well, you are to a certain extent. And so one thing that can go wrong with thermal evaporation is that you get like particles of metal that eject that aren't in vapor form, but actually kind of a, you know, not like that. I mean, you might get an actual particle of gold that comes spitting off of here and then hits your wafer, and then basically that's not a nice thing. I mean, you don't want things like that. And so electron beam may you know, not have that problem as much as thermal evaporation. I guess when it comes down to it, I want you to be aware of both types. Of course, I want you to view the video where Nam operates. He does an e-beam, I think, and understand how they work. Of course, you know, all this is in vacuum. Obviously, if it weren't in vacuum, that vapor would scatter off of any atmosphere and not form a nice thin film. And okay, let's move on. So what are we up to here? All right. I think what we're going to do is we're just going to do physical okay, we'll just do the two different forms of physical vapor deposition. So one, evaporation. And as we discussed, that's basically where you simply heat up the material to be evaporated until it essentially boils and comes off as a vapor. And you can heat it either through resistive heating or through e-beam heating. And the second one is sputtering, which is shown in this figure here. And basically the difference is that sputtering, I haven't done sputtering so much myself in the lab. I've tended to use evaporation to deposit thin films. But sputtering, the process is different. You're not heating the material to be evaporated, but instead, and let me do this down here, you're taking usually a beam of ions, usually argon ions, and you're striking a target. And it's just what it sounds like. You're not evaporating. I mean, this is, and it's shown upside down, which it usually is in sputtering. That's one of the nice things about sputtering is the wafer can just be down here. The sputtering target can be up here. And you're throwing a beam of ions, usually argon, and you're basically knocking the atoms off of the material to deposit it, and then they come flying off and go onto the wafer. Now, why might you want to do that? Well, I think we'll save that till next time, because we're running up against you know, a little bit of length here. But you can see the fundamental difference is that for sputtering, the target can essentially be, you know, much colder, and so you're not going down with nearly as much thermal energy as you are with physical vapor deposition, and so there's reasons why you would form a thin film sometimes using sputtering, because of that difference in the temperature of the atoms when they hit the surface. Now, I forget whether he talks in here about the, I mean, basically what it comes down to is that there's certain things that can be evaporated better with sputtering versus evaporation. But you know, it's sort of said here, in sputtering, the film tends to adhere better and have and be denser. But it's I guess the way I'll leave this is that sputtering is something that you have to spend a lot more time on developing the recipe, because it's there's a lot of things you need to take into account. The ion energy, this talks about sputtering yield, which basically means the number of, I mean, for a given sputtering atom, how many atoms of the material are actually put into the film, and all that results in that sputtering tends to have a lower deposition rate. So I guess you know, he doesn't really do it nicely here, but I think generally sputtering can give you a denser, more adherent thin film, but at the cost of taking a longer time, basically. So, and the other thing I'll use is sputtering is kind of more complicated. Evaporation is easier. Sputtering is typically used in actual, you know, like Intel, because you can make larger machines essentially. Evaporation is typically limited to smaller machines. It's hard to make them bigger, and so put bigger and more wafers through it. So in your research activity, you'll tend to use evaporators, whereas if you go out and work for Intel, what you'll see are sputterers. And I'll just leave it at that for now. Okay, I think we're going to quit there. I mean, as said, besides physical vapor deposition, where you're physically producing a vapor, there's chemical vapor deposition, and we'll talk about that next time. So this is the extent of the lecture for this week, and what what I'm hoping to have happen is that at least by Thursday's chat me session, let me put it this way: one way or another, I'll get you the video, the evaporation video, so that you have that. And one way or another, I'll get that to you before Thursday, so you can view that as well as this lecture. Okay, that's it for today. Thank you.